today's agenda are here. So we are gonna do introductions and why Python, why scripting, and then what's the general workflow, and then the meat of the workshop is gonna be about two Python packages essentially. First is pyradiance, and then that's just a bare bone wrapper of Radiance in Python. And then after that, we're gonna do frads. Frads is a more monster package that it encapsulate a lot of things. We'll see how far we go in that. So why scripting? There are two, I think, objective reasons. One is customizable and reusable workflow. So when I say scripting, I'm saying in contrast to workflows that involves a GUI, maybe even including workflows like Rhino with Grasshopper. So when I say scripting, this is purely text-based scripting modeling workflow. And then the scripting will give you more control over how the actual computation is actually carried out for your individual needs. The third one is more subjective. It's just mentally, or in a metaverse, this is one last layer between you and then the metal, because depends on how you feel. There's always a GUI layer that can introduce confusions or even bug, or just maybe not as productive as you can be. And why Python? Python is kind of beginner scripting language, and it has a very rich ecosystem that we can play with. And given thanks to all the artificial intelligence, machine learning, or computer graphics developments, that we can leverage a lot of things that's already been done. The general workflow is kind of a linear, similar to how you would do it normally with a CAD software. So you would do model authoring. So you build your model any way you want, with a CAD or with Jambox or Jamsurf. And then once you're done with that, that's kind of, there's a distinct breaking point that you're gonna move to a purely text-based environment to do all the engineering, simulation, analysis, visualization, all kind of things. So you can kind of go back to model authoring once you authored your model. It's not as ergonomic as I think it can be right now. So I'm just thinking of this as a linear process. So you build your model and you go to the scripts world, and then you change your model again and you go to your scripts world again. So that's how I think of this as a general workflow. So we're gonna jump right into pyradiance. The pyradiance come with battery included. So what I mean by that is it includes radiance. So what the motivation behind pyradiance is, a large part is helping people having access to Radiance without having to learn how do you set up your path, how do you install Radiance, with the general most common questions asked. How do I install Radiance? And also, once I install Radiance, where is it? Hopefully this helps address some of that. So all you have to do is pip install pyradiance, but don't do that yet. So essentially, when we install Radiance, it just come with all the libraries, executables that we package together in a nice package that can just deliver to your machine. So any Windows users here? Let's see a couple. Okay, so for Windows user, we highly recommend you to use WSL, which is Windows Subsystem Linux. So it's very simple. All you have to do is open your command line and run WSL space -- install. And then with that single command, you have, I think it defaults install Ubuntu. And then once you have that installed, you can enjoy multiprocessing. The process is relatively simple. And then the speed that comes with it is just, I think it's worth it. But it is one extra step. So for all the Windows users, if you want to use WSL for the rest of the workshop, please run this command. It's going to take a while. I think the internet speed here is not great. I don't know how long it's going to take. Maybe we can, yeah, run that and then maybe after lunch it's done. So yeah, so that's that. So the rest of us that don't use Windows, we can, or don't want to use the WSL, we can just go to this URL. And then if you're familiar with Git, you can git clone that repository to your local place. If you're not, you can just download the zip. The zip button is right here. So in the green button, there's a code, and then you can see at the bottom here, this download zip. So yeah, so it's two options. But if you're using WSL, you have to use git clone. You don't have to, but it's the easiest. Essentially, you have to go into a WSL and then run the git clone command. So I'm gonna wait and then see if everybody's following along. Good? Good to move on? Okay. So we're gonna do best practice here. So the best practice when you're working with Python is you create a virtual environment. The reason to do that is to just keep things tidy. You don't pollute your global environment. So that's why some of you already pip installed pyradiance. If you run that without using a virtual environment, you basically install that globally. So that the upside is that you don't have to reinstall again for other projects. The downside of that again is when you install a package, it might comes with other dependencies that you don't want other project to have access to. That don't happen a lot if you're not doing software developments, but it's just a good practice for each project, you create a virtual environment and then you just install everything you need for that project. So this is how you do it. Forever. So it's just you activate it and then you just only use the stuff that's installed in the virtual environment and then you deactivate once you're done. And then you can delete it and you can recreate it. Doesn't really matter. Yeah.
Downloaded the latest Python to Mac, Python.
Yeah. Yeah. So my command here says Python. Some of you might have to use Python 3.
Then it said no module name.
Yeah. So yeah. So I guess all the WSL installed is still installing. So all the other users will have to use source .vmv/bin/activate to activate your virtual environment. Again, you don't have to do this. It's just trying to follow best practice here. So, and once you've done that, you can run pip install notebook and IPY kernel. Sometimes the IPY kernel comes with a notebook, but be nice to run that. And once you've done that, you're gonna ask Jupyter Notebook to use the virtual environment you just created. If you think you have everything installed and ready, you can just type in Jupyter Notebook at the root directory of the project folder that we downloaded from GitHub. If you are using WSL, you need to add no browser. It's bigger. That help? Yeah, so if you are on WSL, you need to add no browser. Otherwise, you can just type in Jupyter Notebook. And then that should open up a browser with things like this. If you're seeing this, you're good. If you're using WSL, you're gonna see a link like this. And then you click on the link or copy paste. I don't know if click on it works. If it doesn't work, you have to copy paste this link and then paste it into your browser. That's if you are on WSL. If you're not on WSL, you just run the command and then the browser will open up automatically. And then it will be like this. Yeah, just the directory of the file. For WSL only. Just Jupyter Notebook. If everybody's good, then we're gonna open the pyradiance walkthrough by double-click this. And it's gonna open another tab that's gonna look like this. And we can just run through them one by one. The first one is importing all the necessary package that we're gonna use for this walkthrough. If you run it, you can just make sure that it is highlighted, this cell. The way that it's highlighted is you can see a blue bar on the left. It means that this cell is highlighted. And then you can move up and down with your arrow keys. If you want to edit anything, you can just click on the cell and that will be in edit. And you can change things. But for the first cell, we can just run it. So to run it, we can use either shift command or shift return or this run button here, play button here. If you run it, and it's gonna jump right through. You can see the run count here is 2. It means this is the second thing we run. So we sort of just run it twice. So if we run this cell and nothing shows up, that's good news. Just the first one, the one that's, yeah. 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 Hmm? Yeah.
Daytime was not installed before.
Daytime should be automatically. Radiance. Okay, you're not using the pyradiance, your virtual environment.
Oh,
So go clear, yeah, exit out the whole thing. Control C, control it twice. And then Python -n ipy kernel. Yeah.
on overwrite.
Oh, let's change that. This is revert. Yes.
Revert.
Yeah.
Okay. Thank you.
Looks like it's working.
Yeah, all of these loaded, there were no errors.
Okay. So this one, I think he changed it to non-code. So if you go down cell. Okay. Now it's good. Yeah, so this command tells the notebook before you run it, that tells the notebook to use your virtual environment if you are using a virtual environment. If you're not using a virtual environment, you don't need this. Good, good. We're ready to move on to the real stuff. So first we make a scene, literally. So the first command is pyradiance scene command. It's just kind of like a helper class to organize your scene files. So it's organized by surfaces, materials, sources, views, sensors, that kind of stuff. So if we just run this thing should work straight away. So the first thing is just we're creating a scene called my scene, and then we call it my scene here. So that's we call it the ID of the scene, and then surface. So we are loading a room.rad surface file. So this is a list. That means you can add more stuff to it. So for this purpose, we just have a single file called room.rad. And then materials is the same. It's a list of strings. So we have a single file called materials.mat. You can add more stuff to it. The order of these surfaces and material doesn't matter. It's just yeah. So we created a really preliminary scene here. The second part is my view. We're creating a view. So view type is A for the equal angular fisheye, and position, direction, horizontal angle, vertical angle. That's pretty self-explanatory. And then we can add this view to the scene that we just created. Next, we create a sky. So we are using the time we have now. So whatever time we are running, 1:43. We are calling gen_daylit with that time, and then latitude and longitude, direct normal and diffuse horizontal. So the way to check the function signature on Jupyter Notebook is you can do multiple things. You can have your cursor highlighted in the function you want to look at, so you don't know. So you can do, for example, I'm gonna do pr is how we imported the pyradiance. So we import pyradiance as pr, so that's kind of our short name for pyradiance, so we don't have to type pyradiance every time we want to access it. So we do pr dot, and then you just hit tab. It's going to load up everything that we can have access under pr. So basically all the Radiance commands, all the common Radiance commands are here. You can see. And then when we know we want to use gen daylid, for example, to generate sky, we can do gen. Then you can also type, and it's going to show you all the gen command. And then you can do gen d, and it's going to narrow it down to gen daylid, gen day matrix. And then if you see this is the one, and then you just hit enter, and then it auto completes that for you. So once you get familiar with this process, you don't have to manually type everything. So everything can be auto completed. But now you don't know how to use gen daylid, right? You don't have to go back and Google it and then search how do I use gen daylid. You can just do shift tab. So when you do shift the tab, when the cursor is in that function, it's going to show up the function signature of this function. So it's showing you that it takes all of these things. Some of them are optional. Some of them are mandatory. So first is daytime, latitude, longitude, time zone. Year is optional. Diffuse, horizontal, direct, normal. All those are marked optional. And some will have a default value that you can override. So that's one way. So you also have a doc string at the bottom that is kind of an English explanation of what this function does. So basically explaining what each argument is, latitude, longitude in degrees, and so on and so forth. So this is one way to check the function signature. It's shift tab. The other way is to type a question mark right after it. So when you do pyradiance pr.gendaylid question mark, it means that I don't know what this is. And if I hit run it, it's going to show up the same thing. In a more, so you don't have to look at the small window, and then you can copy and paste and so on and so forth. But if you want to know the source code, if you're that curious, you can type another question mark, and then you run it, and it's going to show the source code for that function. So that's one nice feature of Jupyter Notebook. It's too small. That's better. So yeah, so that's how we use it. So for any function you're curious, you just do one of those three things to look it up. But you can get if you already know the Radiance commands, it's going to be very similar to that. So yeah, so essentially we run. So this is where we run gen daylid, and then we can just run it now and see what it looks like. So we just open a new cell below it. So open a new cell below it is just, you can hit this plus button here to open a new cell. So you can add stuff to it. So we add a new cell below it, and then just anything but just our gen daylid command. So we can run it and see what it looks like. If we hit the run button, it says, okay, I didn't run the whole thing, sorry. So DT was not defined. So now I defined it, and then you run it, and it's going to show you the actual gen daylid output. So this is just raw bytes that's being visualized in string, but it's actually a bytes. So what this command does is to parse that command raw bytes into primitive. So we do parse, same thing, we can tab, and then if we type parse, there's only two parse function. One is primitive, and we're going to use that. And then parse primitive only takes a string, so we do encode, decode to convert the bytes to string. And then once we parse that, once we run that, we get the three primitives that we have in the output. So If you're familiar with the output of Jane Dillard, it's just like 3. If you have the sun, and then it's light and source, and then the last is a bright funk. That's your sky funk. So it basically parsed that entire primitive, and then basically this for loop is basically just going through each of these primitives and add that to the source of our scene. So once we have that, just gonna get rid of this for now. So basically we're gonna add the old sky glow and then source and then all that kind of stuff. So this is how you hand row a primitive. You just type in the modifier, the type, the identifier, and then the string arg. The string arguments, in this case, is empty, just empty list. And then the real arguments is just the actual arguments. We don't have to give it how many arguments we have. So once we run that, and then we can just render an image. So we can just hit render and take a few seconds. Okay, so here we have a number of processes 8 here. You can change it. If you're using WSL, this will work. If you're not using WSL, this might or might not work. You might have to change it to 1. Sometimes it works, sometimes, but it doesn't work. You just gotta have to use 1.
So where is the multi-processing?
If you're WSL, it's happening inside WSL. Yeah, so the render function is actually using RTPict. It's using, yeah. And then it's using, the render function is using RAD programs to automatically grab all the parameters for you. So you see the quality here, I'm setting low. That is the quality parameter that's being passed to the RAD program. And the RAD program will look at your scene and automatically figure out what's the low setting for your scene. So you don't have to exactly know what is ambient super sampling, ambient divisions, all that kind of stuff. So the only thing that you can directly control here is ambient bounce, and then you can also directly override the parameters if you know what you're doing. But yeah, the quality here is kind of, you can change it to medium or high, which is going to take a long time. So we stick with low here. Yeah. Everybody's good so far? Okay. And then now we rendered our image. You can try to see what does the image variable looks like, but I wouldn't recommend it because it's going to be just a bunch of bytes. So how do we see that image if we don't want to use XImage? So at this point, you can just go outside of Jupyter Notebook and then use XImage to open it up. But if we want to visualize it inside of Jupyter Notebook, we'd have to tone map it first. So this is a kind of a long process because Pecan can only take a file. So we have to write our image to a file first. So this is how you write an image to a file. We open a file called raw.hdr. And then we're going to write a bunch of bytes to it. And then we write a bunch of bytes, the image bytes, to our raw.hdr file. And then this will automatically open and close the file, so you don't have to worry about that. And then once we have the raw.hdr files actually written in our file systems, we can call Pecan to do our tone mapping for us. We're using human equals true. So that's the human adaptation filters. And then if you're curious about Pecan, you can just click on the Pecan and then do Shift Tab. And then you have all the options available for you. And along with the documentations of what each variable means. So we did a human equals true, the mimic human visual response. This is the same. So basically, a lot of verbiage are copied over from the man page, and then just listed it out here. And the other things that so when we run the pcon, and then the next thing we want to know is the dimension of the image. So we can use get info to get a dimension of the image. So get info of the image, and then we say with dimension only. And then here we get the X and Y resolution of the image. We convert those to integers because what you got here is strings. And then we use p-value to get the tone mapped image, the pixel value of the tone mapped image. So here we have a bunch of tags that we have to pay attention to. So the idea here is we want to get the raw pixel values of an image. The reason for that is the visualization process in Python is we're using libraries to visualize basically each pixels. So we have to get the actual pixel values. So p-value comes really handy here. And then we don't want the header, and then we want the output to be binary. So this is key. We want the output to be binary, not ASCII. And then we want a single precision float, and then we don't want the resolution string. So basically, we just want the raw pixel data. And then that's our image data. And then we use NumPy. Now we're using a really popular external library that is working with numbers in Python. So we're going to load that from buffer, our raw image data, and then we're going to tell them is that it's a NumPy single precision. It's a single precision data, and then we're going to reshape. So once we run the NumPy from buffer, so it's going to be a single row data strings, but we want them to be essentially a matrix of data. So we want to reshape that into our X and Y resolution and 3 channels. And then we can do, so this is our visualization memory. We're going to show an image. So that image is our image array we just defined here. So if we run that, this is what we have. This is what you have.
Would it have been possible to just for it to get first
Yes, I'm just showing a really fast way of doing this. There are definitely, yeah, as you can see it, you can convert the tone mapped HDR to other format and visualize directly. But the advantage of this is the key image underscore array that we loaded from NumPy. So this can be used basically universally to any other libraries. Most of the libraries you have in Python world that, for example, if you want to do denoise, if you have a lot of noise in your image, you want to denoise it, you can just directly pass this into that denoiser functions, and then you will just take it immediately without it. You don't have to modify anything. So that's one advantage of having the data in a industry standards array object that can be just passed around to any other stuff that you just click the play button. Is everybody seeing this image? Okay. So this is a tone mapped image. And we want to look at the false color luminance value. So again, we can go back and then leave this terminal and leave this notebook and go back to terminal and then call false color. But we're going to show the entire workflow here that you can do here, for example, to look at the false color. The same thing, we're going to directly run the p-value on the image that we render. So this is not tone mapped, as you can see here. The same exact command, we're just grabbing the raw data and then load that into a NumPy array. So now we have an image array. And then to get luminance, you get your usual coefficients. You multiply the red channel, the first channel, by 47.4, and then so on and so forth. So this is essentially, we're directly manipulating on the NumPy array here. So this is really fast. And then this is how you get a luminance value. And then once we have the luminance value, so we can actually, so we can run this, and then you can see we're using the, so this is all comes free with the Python visualization library called matplotlib. So we're visualizing the luminance value using a column map called the viridis. And then we want our scale to be log. So if you don't have this, it's going to default to linear scale. I'm just showing that you can just set the normalization to log norm here. And then we can also add a color bar that's going to show. So if you run this, I didn't run this. If you run this, this is what you're going to see. Is everybody seeing this image? I'm sorry? No, it doesn't save files by default. So you have to explicitly save the file here. Yeah. Yeah, by default, all the memories or all the results are saved in memory. So you can just directly use for the next functions, unless it's pecan, something like pecan that has to take a file, then you have to write it to file first. But if it's something like a pfelt, you can just directly pass the raw command to the pfelt, and then that gets pfelted or pcommed. Anything that can take anything from standard in, essentially, we can just directly pass it in without writing it to a file first. So this is what it looks like. Everybody seeing this? Good. We move on. So so that's just the overview of a very simple workflow, hopefully relatively simply, of rendering, making a scene, making a render, and visualize it. So as you can imagine, you can basically reorganize all of these into a single functions that you can save, reuse. You don't have to type this whole thing every time you are visualizing an image. You can create a function that's your for you to explore how do you if you're not familiar with scripting, you can write a functions and then reuse it later. So that's hopefully that's the beauty of it. So I'm just showing the whole thing here, but you can basically see that this whole thing can be a single function. You can basically call it something like tone map, visualize tone mapping, something like that, right? Tone map, and then you pass the image data, and if you run this whole thing, you just basically copy paste this whole code into this function, and next time you just have to run this whole function on the image data, and it does the same thing. So that's the idea. So now we can look at another kind of useful things that we do is we have a sampling parameters objects. Again, shift and tab to look at things. If it's sometimes we don't have a string, sometimes we do. Most of the time we do. In this case, it's just like we don't have a lot of explanation. So it's called like sampling parameters. So we initiate this object, and then we can assign all of our regular radiance parameters to it. So this doesn't look that special. It's just giving a number to a string, but it actually does some kind of a checking, like a preliminary checking. So for example, if I run this, it's not going to complain anything. If I do, I want to set ambient bounce to 0.5. That doesn't make sense. So it's going to complain and tell you that this value cannot be an integer, or has to be an integer. So it's going to say value has to be an int. So you cannot send ambient bounce to 0.5. Similarly, you can send, for example, I can send ambient value to 0.5, 0.8. So I don't type the third value there. Actually, this is comma. And then the same thing is going to complain, says that this value, ambient value you typed here has to be 3 value. You only type the 2. So it's going to hopefully this will catch some of the error earlier, like a typo type of things. We can do more sophisticated checks, but right now it's just like a pretty basic check for validity of your parameters. Make sure you don't make silly mistakes like that. So yeah, so run that, and then this time we can call RTPic directly to render a scene. So this is not going through the render function that we see earlier. That's kind of like a beginner-friendly render functions that you do. So this is after you know what this render function does, you know you're more confident about using actually the tools underneath. So this we do RTPic. Again, you can do Shift Tab and look at the signature of the RTPic. And then what does this parameter do? And then what value does it take? So it takes a view. First, I'm going to give it my view. We just defined it above. And then it takes an octree. So we can just give it the my scene.octree. And then X resolution, Y resolution, number of processors, and params. So params is the ones that we just defined here in the cell above. So basically, we call sp.args to convert our parameters into a list of strings that we can directly use. So this is what it looks like. sp.args it looks like this. So basically, we're generating this and then pass that into RTPic. And then if we run that, so this is going to take a long time if you're not using WSL because we're generating a rather large image. So if you have more cores, you can change from 8 to 16 or 12 or whatever. I probably overdone it with the resolution. So this asterisk here, it means that it's running, it's working on that cell. Yeah, and then once it's done, it's going to change to a number. Let's keep tracking of what's the latest cell you run. I'm still running it with 8 processors. Think about 2 minutes. That's what I remembered. I might be wrong. If it's too slow, we can change the resolution down. Yeah, sometimes you have to change A to 1. Sometimes it complains. It doesn't complain, just like, I'm giving up. Number of processors. No, just running this command doesn't generate any files. So this RTPic command is just running RTPic and then grab the things in memory. So we have img variable here. So this is our actual image in memory. We're not writing any files yet. Finish? I'm still running. Mine's still running. I probably should have changed resolution. So if you're finished, you can continue to the next step. So this is more a compact version of the long list of command we see above. So as you see here, we use pfelt, shift command, shift tab to see. I cannot do that now because I'm running the cell before. So basically, pfelt is directly pfelting on the image in memory. And then we only use 1 pass, and then we're going to downsample the resolution 4 times. So basically, we have 3200 here, and then we can basically downsample this 4 times. Gives us a 800 by 800 image. And then we set our Gaussian filter radius 0.6. So all of these, you don't have to type in one word. Basically, for example, if you do 1 here, if you type 1 and then you just hit tab, it will automatically complete that for you, say 1 pass. Same thing here, you can just hit X and then tab, and then it will automatically complete that for you. So we're basically running this p-felted image into a raw2.hdr file. And then the same thing here, we basically combining multiple comments into a single line. So it's exactly the same as above. And then once you visualize that, this is the image you see. I think this image everybody sees, right? It's automatically saved from before. So, okay, so I'm gonna just cancel this. It's taking longer than I remember. So to cancel a run, you just do this pause button, interrupt kernel. And then it's gonna interrupt the rendering process for you. And then this is too much. I'm going to right click on it and then say clear cell output. So, okay. So this is the image. So it's basically 3200 by 3200 downsampled 4 times. And then with a Gaussian filter 0.6. And this is what it looks like. Okay. So now we're going to move on to a more interesting stuff that it's more challenging to do with the regular command line Radiance. So we're going to do a BSDF analysis. So we're going to run cell one by line. So first, we're going to load a tensor tree BSDF. So we have a pyradiance.bsdf objects. And then we can just run that. Okay, so it's going to complain that we cannot find this XML file. That means the XML file is in the wrong path. So I forgot to change that. It's actually in the resource folder. So we're going to add resources in front of it with a slash. And then if we run it again, it's going to load your tensor tree BSDF into memory. And once it's loaded, it should be really quick. Once it's loaded, we can check the information and the components of the BSDF. And if we run it, it's going to show us the meta information of the BSDF. Is going to show peak front hemispherical reflectance and peak back hemispherical reflectance. And then actually, I forgot to add print to it, so it doesn't look this horrible. If you add a print function to the output strings that we just added, we print it, and then it's a little bit nicer to see. So this is the characteristics of the BSDF we just loaded. And this is the tensor tree BSDF we loaded, and then now we can load another one. We can load a clamps one. Same here, we forgot to add the resources string here. And same thing, we run it, it's going to load the clamps BSDF. This time it's going to be much faster because clamps is a lot smaller. And then reload the BSDF here. So this is all just general information, but now we can start to query the BSDF. So creating two lists here. One is, so we're trying to compute the direct hemispherical transmittance of these two BSDFs. And then the way to do that, and then we want to know what's the angle profile. So we want to know from 0 degree, which is normal incidence, all the way to 90, actually 89 degrees. And then we want to know what is the direct hemispherical transmittance of these two BSDF at each incident angle. So we create two lists, one storing the values of our tensor tree BSDF, one storing the values of our clamps BSDF. And we run a for loop here from 0 to 89. And then we're going to append so this is the function that we call that directly queries the BSDF of our BSDF in memory. So the first variable is the the incident angle in theta. The second is incident angle in phi. So in this case, we just give it a 0. So we can get incident angle theta and incident phi 0. And we want to know the transmittance. So just T itself is going to be hemispherical transmittance. But if you add the TS here, that's going to give you the specular transmittance, and TD here for the diffuse transmittance. So if we just do that and we run it, it's going to be instantaneous because all the stuff is already loaded in memory. So all we do is query. And then now we can plot it. So we're using a plotting libraries in Python. Nothing special here. We're just going to plot our tensor tree hemispherical transmittance. We're going to label it T tree, and then we're going to plot a clamps hemispherical transmittance. And we're going to label it clamps. And then we're going to give it an X label, a Y label, and a legend. So if we run this, it's going to give us a plot. That's the direct hemispherical transmittance of the tensor tree and clamps. So as you can see, the clamps has a big step, as you would expect from the clamps resolution. So this is something like 10 steps from 0 degree to 90 degree. And then the tensor tree is more higher resolution, as you can see in the blue lines here. Yeah.
How do you find out what number?
If we do shift the tab here, it doesn't show us anything. But if we do PR, I never tried to find out this. Maybe we can add a 2 question mark. So it's gonna give you the whole member functions in actually source code. So it's probably not helpful for beginner. But I think you can do T tree. If you do T tree and then just hit tab, it's gonna give you the whole thing. Give you a list of things you can call. T tree dot and tab. So it's gonna say, I want to access all the member function of T tree. I don't know what they are. I just gonna hit tab, meaning like tell me all the stuff that I can call. And then it's gonna give you all the stuff that you can call. So that's the BSDF analysis. You can do all sorts of stuff with it. I'm just showing like a simple example of direct hemispherical transmittance querying. You can basically build your own BSDF visualizer with it. Yeah, so imagine this is a BSDF surface. This is your shades. This angle is theta, and this angle is phi. I'm not looking through all the phi angles. I'm just interested in from normal to 89 degree. But you can looking through all of it as well. You can looking through, for example, we can do for I in range 90, and then we can do for J in range 360. So then we can looking through all the phi angles, and then so change this to J, and then we can look through all the 360 phi angles, and then for each of those we can look through the 0 to 90 degree theta angles. Okay. So now we can generate a spectral sky. So this is the new stuff that we just developed. We call very similar to Gen Daylit. We can just use Gen S sky. That's Gen spectral sky. The S stands for spectral. Daytime again, same. So latitude, longitude. This is Salt Lake City. Number of threads. So we're just using 8. And then if we run it, it's gonna using A threads to do the pre-computation to compute all the atmospheric scattering for us and generate our HSR image. Hopefully this doesn't take long. So this and threads is actually threads, it's not processors. So this will work both on Windows and Mac and Ubuntu. You don't have to use WSL in Windows to use the threads here. So it's finished. And then same thing, we do our like standard processes, Skyglow and source and so you can imagine you can basically encapsulate this into a single functions. And then we can write an octree. So in this case, I'm just writing a sky octree. So basically here we're using oconf here. You can do shift tab oconf, and then that will call oconf. So notice that we're not writing any files. So all of these are in memory. So we're basically just gonna pass everything to standard in. So we're gonna pass one by one. So the order here matters because this is the order that Radiance will take. So the S-Sky here we developed is the first one. And we're gonna add sky glow, add a sky source, add a ground source. So that's all of our information to the oconf, and then you run octree, and then you write that to a file. And the rest is empty. So you can do whatever you want with the octree, and then you can write another octree with your geometry, and then you can visualize your, you can render an image with a spectral sky essentially. So that's the end of the pyradiance. I just left it empty for you to try something out first. I think I'm gonna take a break, or we can, yeah, sure, yeah. So you can explore, and then next we're gonna move on to frads. Okay, so move on to frads. So this is a bit more exciting. So very complicated. So this is the layout of frads. So this is a supposedly have everything you need. So batteries of the battery included. So frads consist of 4 major modules. Pyradiance, which is the one we just saw. PyWinCalc. So this is the if you're using LBL window program, this is the equivalent of that. So, and then we have EP model. So EP model is, so the left-hand side is all the optical stuff that we are interested in. On the right-hand side is all the energy stuff that we are also supposed to be interested in. So we have EP model. EP model is energy plus model objects. So this is, as you can see later, so I will see. So, and then Pi Energy Plus. Pi Energy Plus is a package that we built that encapsulate Energy Plus. Similarly, how we encapsulate Radiance in pyradiance, we can encapsulate Energy Plus in Pi Energy Plus. So when you install frads, this is all that comes with it. So if you haven't pip installed frads into your virtual environment, now is the time to do that. So all of these commands are the same as before. So except the last one is that instead of pip install pyradiance, we pip install frads. So now we're ready to open this file that we saw earlier. Yep. So all of these before are the same. So the last line is pip install frads is the key one. File. So double click on the frads walkthrough. Okay, so very similar. Run the first cell that's going to import all the packages we want to use. This is going to take a few seconds because Energy Plus is huge. Our first task is actually not Energy Plus related. We're going to compute the horizontal monoptic logs. So slightly different commands, basically the same. So we're going to make a scene. You can change this. We're going to load the floor rad file. We're going to load the walls.rad file. We're going to load the ceiling.rad file. And then we're going to load our materials into material. And I'm going to load a source. So this is a spectral sky. that I generated and then prepared it in the folders. If you run that, so it should be run really easily. So one thing that we can like enjoy with this type of thing is if we actually have a typo, say I deleted a 0 here, if we run it, it's gonna command, it's gonna complain, says I cannot find this file. So that's another like a convenient features to avoid typos early on in the process. And if we add that back in, and then gonna give it scene, and then so that's our scene there. So with the spectral sky, with all the surfaces and materials ready to go. So we're gonna generate a grid from the floor.red files that we had. So we're gonna grab the floor primitive. So frads comes with this nice unpack primitives functions. So previously we have to parse the output string of a command to get the primitives. Here we can just directly do unpack primitives on a file, and that's going to give us the floor primitives. So in this case, we only have a single polygon in the floor.red file. So we're just going to grab that one. So that's our floor polygon, and we're going to parse the polygon. So this is parsing the polygon type of the radiance primitive. So if you do shift command, this is what it does. A shift tab. And then we're grabbing the first primitive in this file, which is our floor polygon. So that's how we got our floor polygon, and then we generate a grid from that floor polygon of a spacing of 1. I don't remember the unit of the model. I think it's probably 1 feet. No, it's probably 1 meter. Anyway, so spacing and so this is, I think, height. Yeah, so this is height. So if you're not sure that you type the right one, so for example, I type HEIG, I can hit tab, and it's going to confirm that, yeah, right, there is a height parameters here. So for this type of thing, you can omit the keywords spacing or heights, just have 1 and then 0.075, or you can include them into better, so you can quickly not confuse which one is spacing, which one is height. So if you run this, it's going to give us a grid. If you're curious what the grid look like, we can add a grid, add a cell below, and then we can see, just visualize the grid. So that's our grid, X and Y and Z position and the direction. Okay. Now we're ready to trace, generate our horizontal. So that's a horizontal grid. So we're going to generate a menonopic lux of that horizontal sensor. So grid race is prepare our grid into a string format that Radiance like, and then we want 20 samples, 20 bands, and then again, if you remember earlier, we're initiating a sampling parameters objects. We're setting irradiance to true, so we want to know the irradiance, AB, AD, AA, so on and so forth. And we set CO to true. We want to output. We want to force a spectral simulation, and then we want 20 bands for our spectral simulation. And then once we have that, we can just run our trace. And then with our sing arctree, and then here we can see dash PM. So you can see we added a dash PM parameters here. You see, that's telling our trace that we want to convert all the spectral samples, spectral results into menonopic lux at the end. Yeah. Okay. So yeah. So once we have that, we're ready to run it. Should be relatively fast. even with a single processor. Yeah, so it's finished. And then we can visualize it. So just gonna clear this out first. So same thing. So it's less work when we just dealing with straight data, not an image. So we can just straight load the R-trace results. So notice that we also don't have a header of our R-trace results, just the pure data in single position binary. And then load the results from using from buffer. And then that will give us in the NumPy array. So here I cheated a little bit because I know the dimension of the grid. The dimension of the grid is 53 by 61. But you can figure out the dimension of the grid by mathematically figuring out how big is the polygon and then what's the spacing. There's some way to figure it out, but we don't want to get into it now. So I just give you the shape of the grid is this, and then we're gonna visualize it as an image. So we're gonna just directly show the monopic lux, and then it's not, the dimension of it changed since I last run it. Wait a minute. Actually, this is height. The second one is spacing. I flipped it, so I'm gonna rerun it. No, if you give it a name, the order doesn't matter. Because I didn't give a name before. I have a 1 and 0.75. So when I named it, I actually flipped it. So when you don't give it a name, the order matters. When you give it a name, the order doesn't matter. So you should see this image. This is just a linear false color, so it's not really helpful. We're not seeing any details in the lower range. We just like the higher range is just fully exposed, overexposed with like 40,000 lux. The rest is about less than 5,000. Actually, maybe we can change the normal. No. So yeah, so this is just demonstration how we compute a horizontal monopic lux. Everybody's seeing this? Not the one I generated, but you rerun it and then see this. Okay. So now that's just like a short segue. So now we can do phase simulations. So this is a little bit more complicated because we need to give it a lot of information for the automation to happen. So basically, this is how we set up a workflow configuration from a single dictionary. A dictionary is just the mapping of information. So a name and the data. And then, so this is one way to do it. So basically we set up a single dictionary of the information we need to carry out the entire three-phase simulation, for example. You can click on the link here to see another methods of setting up this workflow that we don't introduce this as a single dictionary, but we can construct a component of it one at a time. So settings, so all of these are, so some of these are optional, some of these are mandatory. So for example, EPW file and a WEA file, you need one of these. Otherwise, you wouldn't know where the weather data comes from. And also, what are the sampling parameters we want to use for each type of the matrix. Some of it are irrelevant to the methods that we use, but if you don't do anything, it's going to have a good default value. So here for the speed purpose, we're just going to set everything to AB1, and then hopefully that runs fast. And then number of processors here, I use 32, which is probably too much. But if you're on Windows, this is going to be 1. If you're on Windows WSL, it's however many processors you have. And then here I have a tag here. You want to save matrices or not? So if you set it to false, everything will be in memory. So everything will be in memory as much memory as you have. So for example, if you're doing a 3-phase image-based calculation, which involves hundreds or thousands of HDR file, then it's gonna write a out-of-core memory file to your local drive and then load from there. But if you say I want to save the actual data, it's always gonna save it. And then when you, so the nice thing about this, so if you hit save matrices equal true, and then if I just rerun the whole thing again, it's gonna check, did you change anything in this entire configuration? If you didn't change anything, it's not gonna rerun. It's just gonna grab the same results that you have. So it checks the file modify, so same as the make file. So you will check when did you last added this walls.rad. So it's gonna store all the files last updates, either in memory or in file to a hash. And it's gonna check the hash against every time you load it. It's like, did you change it? Did the hash change? If the hash changed, rerun. If the hash didn't change, just check for results. And then, so similar things we have in the model category. So that's setting category. That's relates to simulation settings. And the other part is model. So within model, we need to define scene. So that's usually non-Windows opaque surfaces. And then we have Windows. For Windows, we can have multiple windows, window 1 or window 2. Here we have the window file, and then we want to give it a name to this matrix, during the matrix operation, we want to give it a name. So we want, what do we want to refer this window to when we do the matrix calculation? And then in the materials file, materials objects, we can have files. That's all of our material definition. And the matrices. Matrices is all the BSDF files we want to store. So as you can see here is a dictionary. So for window 1 matrix, as you can see here, both class is called the window 1 matrix. For window 1 matrix, we have a single matrix file that is this clam's BSDF. We can have multiple. Right now we only have a single one. We can have more than one. And then that's when it comes in that we want to dynamically change the window shade type during simulation. That's how we refer to the BSDF. So for example, for window 1, at each time step, I can grab this BSDF instead of the other one. So sensors is what kind of sensors we have. So right now, I'm just going to do a single sensor, a horizontal sensor. And then once we have all the pieces ready, we can just generate the workflow configuration. So this is a method that generates the entire workflow configuration from a single dictionary. So once we run that, and then we are ready to initiate our 3-phase methods. So run that, and then loading our workflow, setting it up. And then this is where the time-consuming parts come in. And then, so this is our 3-phase workflow essentially. So, so we can do a member function. So this workflow has a generate matrices. So no matter it's two-phase or three-phase, for example, you can change that to two-phase, and then the same thing will work. You can change that to five-phase, and then it will work as well. It should. So three-phase methods, workflow, and you generate the matrix. So it will run, and then once it's finished, shouldn't take that long. So this is the process of generating all the view matrix, the daylight matrix, and then getting all the sky matrix ready. So all the standard workflow. Okay, mine's finished. So finished generating all the matrices. If you are curious of all the matrices, you can check it. So workflow dot sensor. So sensor window matrices is the matrices that goes from the sensor to the window. So that's our sensor window matrices. It's a matrix objects. If we do the dot operator again, and then we can see all the things that we can check. And one of them, so it's actually a dictionary. And then remember we named our sensors earlier. So our sensor is called a view one. It's kind of confusing. But anyway, so the sensor is called a view one. And then we're gonna give it a name. We're gonna query the view one sensor to window matrix. And that's gonna give us a matrix file. And if you hit dot array, that's gonna give you the view matrix in NumPy array. So this is all the matrix multiplication happening in NumPy array. So this is all in memory. So for example, if we want to check daylight matrix, so we have two daylight matrix, one for each window. If we hit window one, that's going to be a window one matrix. If we hit an array, that's our window one daylight matrix in a NumPy array. So yeah, so that's how you find out, like, you want to know what's the actual data. And then if we don't care about any of that, we generate our matrix. Now we can calculate it. Calculate meaning just multiply them together. So we want to calculate the sensor. The sensor name is view one. For the BSDF, we want to assign window one to window one matrix, window two also to window one matrix. Remember above, we named the matrix to window one, well, to window one matrix. And then we give it a daytime. So this time we get a January 1st, 12 o'clock, direct normal, diffuse horizontal. So when we run that, that will give us the work plane illuminance of that sensor at that time. And we can quickly run another two-phase simulation just without changing anything using the same configuration file. I'm going to name it a workflow 2. You remember before we initiated three-phase methods. So without changing anything, we're going to initiate the two-phase methods. And then same thing, I'm going to generate the matrices. Oops. View one sky matrix is not a file. Oh, okay. So this is the thing that I just mentioned, because we didn't change the configuration file, so you didn't actually rerun it. And then because we use the two-phase methods, in this time it's checking a different files and to say, okay, you didn't change anything about the model, but I'm looking for this file in the results. It didn't exist. So the thing to do is just to restore your kernel and then rerun the first cell and then scene. And then that's it. There is. You can change the name of the, for example, there's a name in the setting. So you can always just change that. So if the name is different, then the hash is different. So so there is a name field here. You can try to set the test, and then another configuration you can just change the config settings.name to test2, and then basically you don't change the rest of it, and then it should be able to force a rerun. So we just started it, and then we can do another. Oops. Run this, and then two-phase generate matrices. Ooh. What's going on here? Still not rerunning. Yeah, so because we use the safe.true, safe matrix.true, so it's gonna always look for the saved matrix file. So I just set it to false. So it's gonna grab the matrix in memory. Now it's gonna force that rerun. And then the same thing we can do calculate sensor. And that's gonna give us a work plane illuminance of it that time. And so if we want to do annual calculation, so remember we give it WEA files early on. That's weird. So workflow do the calculate sensor from WEA, you can see here. And then check. So all we need is a sensor name. So view1. And that's going to calculate all of our annual. So there, as you can see, it's pretty fast. If you missed that, I'm going to show you again. So this is an annual calculation for the entire year. So that's how fast it takes, because everything is already loaded into memory. And then we're using multi-threaded matrix multiplication to calculate an annual work plane illuminance for that sensor. Any questions before we move on to Energy Plus? Weather files. So yeah. So EPW to WEA converts the EPW file to a WEA file. So this is all the interesting part of frads that is working with Energy Plus. So essentially, how does Radiance play with Energy Plus? It's not just a preprocessor. So Radiance obviously can be a preprocessor to Energy Plus, meaning you can pre-generate all the stuff the Energy Plus needs, and then feed that into an IDF files or Energy Plus model. But here we're talking about a more integrated experience between Radiance and Energy Plus. So here we go. So EP model, we just remember that we have a EP model module. So essentially we have a method called load Energy Plus model. And we also has a set of the standard Energy Plus prototype buildings that comes with it. So in this case, we're using a small office That is the DOE prototype building small office building model. So we just run that. So that's gonna load that entire model into objects, into Python. So if we're interested in C, what does that look like? Not letting me. I don't know why it showed up there. EP model dot. It's gonna, and then you hit tab. That's gonna give you a million different options. So that's all of the Energy Plus objects that comes with the model already loaded into a Python object. So this is no longer a dictionary. So if you heard of API before, it is different than API. It's preloaded all the Energy Plus objects into a Python object that you can validate. So essentially what we do here is, for example, if we're interested in knowing what does the window look like, the window in Energy Plus is called fenestration surface detail or something like that. So we can just do fen and tab. So that's the one you found, like just straight away, fenestration surface detail. And then if we run that, that's gonna give us that Energy Plus model, all of the fenestration surfaces. So it has the name, so that's the name of the surface, and then the surface objects. So we can just directly query it. So that's going to give us a fenestration surface detailed objects of this surface name. And if we hit construction and then tab, and it's going to say, okay, there's a construction name field, so you can query. As you can see, the construction name is this. And then if we change to, for example, what is the building surface name, right? What is the name of the wall? Name of the wall is this one. That's the name of the wall where the window surface is. So that just give you an idea, like each object in the Energy Plus model is loaded. And then all you have to do is just directly modify it, change it. And then the nice thing about this is if you messed up in your Energy Plus model, it's going to validate it for you. So if you added something that's not supposed to be, like for example, if a field can go only from 0 to 1, and then you say, I want to set that field to 2 without running Energy Plus, usually that's when you have a bug in Energy Plus model. You set it to some value and then you run it, and then you have to debug the Energy Plus output to figure out how did you get it wrong? Like, because it's a long error output, you're going to see, okay, where did I get it wrong? So this helps you before that. So this is before you run the Energy Plus model. It's going to check your model, validate it against the schema of the Energy Plus input format. So if you have a value of 2 that's supposed to be between 0 and 1, it's going to immediately, before running, tell you that these fields needs to be between 0 and 1. So once we loaded our Energy Plus model, we just set it aside for now. Now we're going to create a glazing system. So this is where the window part comes in. So usually you have to open window, build a glazing systems with your custom layers, generate a whatever BSDF or generate a Energy Plus objects, and then somehow put that Energy Plus objects into your Energy Plus model and then reference your window surface to the BSDF objects. That's usually how you do it, like a lot of manual process of running it, copy pasting, inserting into a text file, make sure it's in the right place, referenced correctly. So here we kind of streamline that process. So there's a single function called create glazing system. So create glazing system is just similar to create glazing systems in window. You add all of your layers. So layers can be glazing layers or shading layers. So this is a JSON files, or it can be an XML file. That's a BSDF. So where does this JSON file comes from, you ask? So we have an igsdb.lbl.gov website that is storing all of the igsdb data. I don't have the login right now, unfortunately. This is a borrowed laptop. But once you logged in, you can basically select the entire glazing and shading database objects. And then you can right-click on the ones you like and download it. And this is the JSON files you have. I already downloaded 2 JSON files, 2 essentially clear glass layer and an electrochromic glass layer. So one is going to be creating a 60% electrochromic glass systems. One is supposed to be 18. So one is called 18% transmittance glazing systems. So to get the logging of the IGSDB, you need to email somebody at LBL to set up an account. No. Somebody. Yeah, I'll put it up later in the slides with your email. Yeah, it's a pain in the ass, I know, but hopefully we're gonna do what normal people do, like have a create account button. I don't think that's gonna happen very soon, so it is what it is. But yeah, I'll let you know how to set up account of IGSDB. There's an API. API is not as useful because you have to know the ID of the objects anyway. So usually just go on a website and then right-click on the ones you like, download it. If you know the ID, so for example, this is the ID 7406. If you know the ID, you can just directly download it with the API using curl or Python or whatever. Download it, wget to download it directly with the API. But yeah, the website is pretty convenient anyway. So we have those, and we can just run it. So this is going to take a little bit because we are doing spectral-wise layer composition. So this is generating a full clamps BSDF of the 2 layers. So this is a full spectrum calculation. Visible solar, and then thermal absorptance, all that kind of stuff. So it's going to take a little bit. And then you can see at the bottom, we do EP model.add glazing systems. So basically, we create these 2 glazing systems, and then we are adding them to the energy plus model, which is loaded. Okay, it's finished. So we created these 2 glazing systems, and then added them to the energy plus model. And we're gonna do our setup. So this is the interesting part. So we do an energy plus setup with our energy plus model, and we want to enable radiance. So this is a keyword that automatically convert your energy plus model to a radiance model. So you don't have to. So for this part, the person running doesn't have to know radiance at all. So you build the energy plus model. It's going to look at every single zone in the energy plus model that has a window. So if you have a core zone that doesn't have any window, it's not going to do anything to it. So it's going to convert all the exterior zone of the energy plus model and then convert that to a radiance model, and then generate a 3-phase calculation to it. And then once we have that, so that's next part is the interesting part. So we're going to set up. So the setup part is going to take a little bit because we're going to generate matrices for every single zones in energy plus model. The gap and gas are default values that you can. So there's a link here. If you go to it, it shows you So this is custom gap. So we can have a gap of 2 different gas. One is air, that's 10%. One is argon, that's 90%. And the thickness of 0.0127 meter. So that's our gaps. So we have a 2-layer systems. There can only be 1 gap. So if you give it 2 gap, it's going to say something's wrong. And then this is how you have define a custom gap with a gas. So that looks like it's finished. So as you can see here, it's validating. It's validating the model. It's going to give you a little bit of warning. So something that it doesn't like. It's not as, so warnings are okay. It's because it's very strict. So it's saying that this evaporative condenser pump rated power consumption objects has a literal of auto size, but you assign it a float. That's not, it's not ideal. It's complaining, but it's okay. So once we have that, we can just run it like that. So if you uncomment this line, just run with the design day, then it's gonna just run Energy Plus as it is without doing anything special. But we wanna call Radiance, right? So we wanna at runtime. So at the annual calculation, at each single time step in our calculation for the entire year, I want Energy Plus to stop and then stop and ask Radiance what is a certain value. So we can do a lot of things here. So this is our, we call it controller functions. So this function, we define it, and this is function that gets called at every single time step during our Energy Plus run. So we can request some values from Energy Plus. For example, here, I'm going to request the surface outside incident solar radiation per area. This is very non-ergonomic, I know, because you have to know this exact string. If you miss the character, it's not going to work. And then I think yeah, so you have to, so basically this is how we get a value from Energy Plus, out of Energy Plus at runtime during simulation. So at this time, so at that time step, I want to grab how much radiation is incident on the window surfaces. So we call it exterior irradiance. And we're going to kind of give the simple control algorithms here. So if the radiance is smaller than 300, I'm going to set the EC to 60%. If the radiance is greater than 300, I'm going to set it to 18%. So it's just a standard heuristic controller. And then we actuate the CFS state. So the CFS is complex fenestration. So that's the 2 glazing systems we created. So we can actuate that. So basically, we can actuate the window to a complex fenestration state. So remember, we named the name of the glazing system. This is called EC_60. This is called EC_18. So basically, that's how we reference that at runtime. So we're gonna actuate this window. The window's name is this. I want to change this window to this state. This state is being set here. We're setting the states to whatever corresponding exterior irradiance. And then once we have that, I can call Radiance to calculate the work plane illuminance. So in this case, it's a very complicated zone. This zone has 6 windows and a door. So essentially, when we did the enable radiance here, we generated for every window, we generated a view matrix here. So essentially, for this calculation, I'm saying that I want to know the average work plane luminance of the zone. The zone name is this. And then this is all of the window. I want to set window 1 to the CFS states, which is which one of these, and I want to set all of them to this. I want to calculate the mean of it. That's the average. So this will give us the average work plane luminance as a result of our changing shades. So our shade changed, and then I want to know what's the resulting work plane luminance. And then I can either do a daylight dimming here, so you can see the stuff in comments here. Like we were checking if people are there. If people are not there, I'm gonna turn off the lights. If people are there, I want to meet the work plane luminance of 500 lux, say. So and then I apply some linear dimming curve saying, okay, so given the shades situation, and as a result, this is our work plane luminance. This is how much lighting power is using. And then I'm actively setting that, overriding the lighting power in Energy Plus. So Energy Plus does its own lighting calculation. I'm overriding the energy calculation. I'm given a more accurate number based on my radiance calculation. And then we can actuate the lighting power here. So that's a simple controller. It's quite long, but you can factor things out. So once we define that controller function, we can set it. So we are setting that controller function to be called at every single time step before predictor. So this is Energy Plus jargon that before we do the system load calculation for each time step, I want the Energy Plus to call this function. So we set that, and then we run it. So once we hit run, it's gonna, for each time step, it's gonna stop, do an average, change the shades based on the control, calculate the work plane luminance, and then if we change the lighting power, change the lighting power, and then do that for every single time step. So if we see, we run this, and then it's gonna, yeah, just run and finish essentially. So the energy, it's still running. So essentially, the Energy Plus results will be the same as you would when you're running a regular Energy Plus simulation, but the stuff can get overridden or calculated, and it's up to you to do whatever you want with the data. I don't know why it's so slow, but yeah, that's basically it. Do you have Energy Plus completed successfully? No? It's probably a server thing. It's not piping the standard out to the notebook. That's interesting. Yeah, never seen that before. Maybe it's still running in the background. Oh, this is locally. Oh, no. No local. Okay. Okay. Any more questions? I know it's a lot. Yeah. So you can calculate glare. So that's one of the standard things that we do. So if your control algorithm is based on glare, yeah. So you would. So we have a function that's called EP setup dot calculate EDGPS. So we have a function that calls enhanced DGPS, similar to how you calculate the double plane work plane luminance. You can calculate an enhanced DGPS to give you a DGP value, and then it's up to you to decide how do you want to do what do you want to do with that DGP value. You can use that to change the shade. So if its DGP is greater than a certain value, I'm gonna tint it down, something like that. You can also calculate solar radiation. So at that time step, you can compute the solar load through the window. If it's greater than a certain number, you can do things. And then the most powerful things that this can do is model predictive control. So essentially at each time step, we're just grabbing whatever the instantaneous weather is at that time step. For model predictive control, at each time step, you would grab the forecast instead. So you would grab the forecast in the next, say, 24 hours. So I want to optimize my current shading operations to minimize my energy bill over the next 24 hours based on the forecast. So if we forecast a heat wave coming in tomorrow, my algorithm is going to say, okay, close all the shades now, even if it's going to use a little bit more lighting energy, and just close all the shades, minimize cooling nodes, and pre-cool the building overnight to deal with the heat wave next day. So that can be used here. So instead of doing this, you do some forecast here. You forecast the weather, and you grab that weather. You can forecast the entire work plane lumens for the next 24 hours, and then you can do some optimization there. You can calculate glare for the next 24 hours, and then yeah, there's a lot of flexibility here. Yeah, you can do whatever you want. So we do optimization, like a really mixed integer linear optimization instead of a heuristic. You can just do, I want to minimize a combination of glare and electricity. And then these are the variables you can play with. You can control the shades, you can tune the lighting energy, and I want to minimize that. You throw that to a Python optimizer, and then the optimizer will do the number crunching. Okay, so this is the best solution you might have for now. For given your constraint, the constraints are like I want a DGP to be smaller than 0.4. I want a work plane luminance to be greater than 300 lux. I want a cooling node to be smaller than such and such, and this is the best solution. So that's more like instantaneous optimization at each time step. Yeah, the controller can call another controller, can call another controller. So it's the possibility is infinite. Yeah. 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 Yeah, absolutely. So anything that can be modulated can be modulated. So any dynamic elements can be changed. They can be changed. So I'm changing the shades here, but usually we have to change the thermostats as well. So to enable pre-cooling, for example, I want the space to be as cool as possible tonight to deal with the heat wave tomorrow. So I'm gonna have to change the thermostats. So not only do I have to turn the window down, I'm gonna change the thermostats to 60 degree to pre-cool the space. And then once it reaches that, and then it's fine. So the things like that, all the energy plus elements that can be changed, you can change here. Yeah. Of the surface. Yeah. 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 You can calculate the instantaneous solar heat gain with the PyWin calc with a realistic environment. Yeah. 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 And then you do a little bit of optimization, right? So you tell Energy Plus use that. Yeah. 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 The possibility is infinite. Yeah. So this is the power of combining Energy Plus and Radiance essentially. Yes, yes, yeah. Other than this type of things. So you either have to look it up in the manual, or you remember this by heart, or you just hard code it into your own personal libraries. Then you give it a name. So you remember that name. You can instead of looking this up, I can just give it a nickname, say surface outside name, and I can just use it next time instead of memorizing this whole thing. Yeah, true. Yeah. Yeah, so the loading of the model, the modification of the model, the validation of the model, so those are coming together to help people run Energy Plus without being a expert in it, because you have to really, when you run an Energy Plus model blind, all you can do is just look at the error message and then figure out in like 1,000 lines of Energy Plus model where did you make a mistake. So here we try to minimize that as much as possible, do pre-validation in every single fields in your Energy Plus model before you run it. Yeah. 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 Absolutely. Yeah, so geometry options, you mean detailed geometry, actual geometry? So yeah, larger overhangs are fine. Are you talking about like a dynamic overhang that can change, like a awning type of thing? Yeah. So awning it can be a BSDF, of course. And then the only thing that matters for Energy Plus is essentially incidence of radiation. So the geometry detail doesn't really matter that much as long as the total energy incidented on the window is correct. Then that's correct. And then you can have Radiance deal with all the detailed geometry for glare calculations and so on. Yeah, absolutely. So those can be baked into BSDF and then feed that into Energy Plus for heat gain calculation, which is going to be plenty enough for accuracy. For radiance, you just do a separate radiance calculation. Yeah. So this is all three phase. Yeah, you can pull it. You can pull. Yeah, Energy Plus. Yeah, you can come from Radiance. It doesn't matter. So here I'm just grabbing the value from Energy Plus. Absolutely. Yeah. Yeah, absolutely. So you can like the ultimate flexibility is that you can place a sensor anywhere you want and then calculate the instantaneous value for the sensor and then just use that. So you're not constrained to anything. Like Radiance doesn't care where do you put the sensor. You put the sensor on the window, on the overhang, outside the overhang, on the rooftop, doesn't matter. And then you just calculate for each simple controller and just calculate the incident radiation on the roof, and then use that to do whatever you want, right? So it's the controller is really flexible. You can do whatever you want with it. But for things like surface temperature, you probably want to grab that from Energy Plus because that's the only place you can get it. So right now, LBNL is developing all the research of multi-fluid controls or advanced control systems based on this framework that basically emulate the operations of a building as closely as possible. So this will give you not only a more accurate energy calculation, but you also get all the other stuff that comes with it, such as DGP or work plane luminance or all the stuff that Radiance can compute. So you do the whole thing and you get both Radiance results and the energy results. Both are supposedly more accurate than just running energy plus. Yeah, yeah. Yeah, and then another thing is, so this AEC16 can be saved. So that's another thing that Windows doesn't have. So you can save this thing, you just compute it, and then send that to your colleague, and then he doesn't have to compute it anymore. And then you make sure that both of you has the same exact glazing systems. Rather than telling your colleagues how to build the glazing systems in Windows, just send them the file, and then also speed up the calculation. Well, you just save it to wherever you want. So you save, I save to a ec16.json file, and then the other person can just load it from these JSON files. Because it is a lot of calculation. Remember, this is a full spectrum calculation. So it's every 5 nanometer from 360 to 2600 or something. So it's a lot of calculation. It calculates reflectance, transmittance, absorptance at every single layer. So yeah, it's a lot of data.